Hello, we're continuing our study of rotational motion with you today, and we're going to talk a little about energy. What is the energy of rotational motion? Let's look at a situation where we have an object that's rotating, is rotating about some axis. And let's say it's rotating at a certain angular velocity. And the question arises, how do we determine the energy of this rotation? And of course, in this case, the formula that you and I have used up to this time as m times v squared divided by 2. It's going to be awkward to use because, again, we can talk about different elements of a given of the body that are at different distances from the axis of rotation will have different velocities. Because this object has the same angular velocity and linear velocity, let me remind you, is the product. The product of the angular velocity of the radius, so different points at different radiuses. Radii will have different velocities. Then how to determine the rotational energy of this object? Clearly, in this case, again, we have to come to the point where we have to, you have to translate that formula into angular magnitudes. And as you and I realize by the analogy that we've used so far, it's quite easy to do that. Because we have a quantity analogous to mass. We've learned about the moment of inertia of an object, so it's also responsible for the inertia of a body. So it shows how much it resists attempts to change its velocity. And then there's also, of course, the analog of linear velocity, which is actually the angular velocity of the motion of the body. Therefore, in order to calculate correctly the rotational energy of any object, you and I will write down the following formula. So the kinetic energy of exactly the rotational motion will now be determined by the formula of the moment of inertia times the square of the angular velocity and divide that by 2. This formula will already work when describing the rotational motion. And here we should not forget that in addition to the rotational motion of the body, can also have a translational motion. And therefore, for cases where we meet, let's say, the same wheel that's moving on a horizontal surface, for example. So there's some translational motion, and then there's some rotation. Then, of course, the total kinetic energy will be defined as the sum of two energies. It's the translational energy and energy of rotational motion. So we can write this expression in this form. So mv squared in half would be the energy of the wheel moving on the road. So it's as if it's not rotating, but say it's just sliding. Let's imagine that. In a frictionless situation, the wheel can't rotate in principle, it just slides like some objects. And in this case, it will just have a translational speed plus some mass. In this case, we get exactly the energy of translational motion. But when we talk about the real situation, of course, we add the rotational energy. And then we have to take into account this rotational effect as well. Therefore, the total energy of rotation or the total energy of motion will be determined by the sum of these two energies. You should always keep this in mind when you're solving a problem for this kind of complicated motion. So that's the thing about the energy of rotational motion. Now, one more parameter that you and I will definitely use in the description of rotational motion is the angular momentum. I will remind you that we have previously met with such a parameter as momentum. It is a quantity that was introduced in the mechanics of translational motion. And we know it as the product of the mass of a body by its velocity. Well, for rotational motion, there's also a similar quantity because when we rotate this object or when we change its rotation, we will necessarily meet with the fact that this object experiences certain resistances or provides this resistance to the cause that causes this movement. And in order to describe this effect, we introduce such a concept as the momentum of a given body. And it's analogous to simple momentum, you see, and it's defined by the product of the moment of inertia of this object by the angular velocity. In this case, it also has its own direction because as angular velocity as well as the moment of momentum are values, are vector quantities. If we look at the dimensionality, here we see that its dimensionality will again be composed of 2 units. And now as far as the units of measurement of this, well, we can see that it's the product of the units of moment of inertia. So it's a kilogram times meter squared. So, and the unit of angular velocity is radians per second, or radians can also be replaced simply by 1, so it's analogous to a dimensionless quantity. So we'll just write it down as 1 divided by 1 second. It doesn't have its own measurement, so we can leave it like that. And let's remember that momentum is related to force in the dynamics of forward motion. So let's write down this expression as Newton's second law of momentum. And similarly, we can write down Newton's second law of momentum, but for rotational motion. Here we have a change in momentum due to the fact that acting for some time upon a certain amount of force which causes this rotation. And again, the momentum is a vector quantity. Why? Because all rotational parameters will be determined by the right-hand rule. We will talk about it in the next lessons, where we will consider the specific reasons that cause the appearance of acceleration of this or that object, and we will consider these rules in practice. But now, at the most important stage, we need to remember that there are laws of translational motion that we've studied, as the laws of kinematics, as well as the laws of dynamics, energy, and similarly to them, we see there is a very good parallel with the law of rotational motion. Therefore, having studied the laws of translational motion, you can easily pass to the laws of rotational motion. There is no problem in it. So this is goodbye. I will see you in the next lessons, where we will dive into the practice and application of these laws in the tasks. That's all for now. See you. Goodbye.